Hey all, Satish here. Today let's see how to use a ADC module. So basically ADC is analog to digital converter. So what it does is any analog voltage which you are feeding into a microcontroller pin, it will convert it into a digital equivalent value. For example, let's assume you have some voltage here and ADC value. So let's see how much bit this ADC is. This is a 10-bit ADC. Basically what it means is whatever the supply voltage or the reference voltage, let's stick with the supply voltage here, and later on I will show you how to use the V reference voltage. Okay, so now my ADC reference is, so my ADC reference is 5 volts. So what, let's assume that you are giving 0 volts to a pin. The ADC value will be, and the resolution is, it's a 10-bit. So basically what it means is it has a resolution 2 to the power of 10 minus 1, that is 1023. So if you give 0 voltage, the ADC value will be 0. This ADC will come inside a register. It's like how we had seen the tris registers and all. Similarly ADC will have its own registers. And if you give 5 volts, that is our ADC reference voltage, you will get 1023. And if you give 2.5 volts, you will get 511. And if you give 1.25, you will get 255. So the formula is your maximum value divided by this into whatever voltage you are giving. Suppose if I give 5, I will get 1023. If I give 1.25, I will get 255. 0.1 volts, this will be the ADC value. So now higher the resolution, better will be your accuracy. Okay, basically what will happen, higher resolution means that 0 to 5 volts you are splitting up into 1023 parts. Okay, then the next is up to 8 channels. So basically what that means is 8 of the microcontroller pin can use this functionality. So they are generally AN0, AN1. So ours is a 40 pin microcontroller. So AN0, AN1, and there are 2 more pins, V reference negative and V reference positive. I'll tell you what this is. Then these are the up till AN7. So there are 8 pins which are capable of having this ADC functionality. Okay, hope you are able to understand this. So now what, where to use it? So now let's assume you want to measure what is the voltage, your battery voltage or some voltage. You can connect it to this ADC controller provided it is below 5 volts. If it is above 5 volts or your V reference, if it is above that, then you have to use a step down converter, like you use a potential divider and then give it to the microcontroller pin. You have to make sure that whatever your maximum voltage, for example the 100 volts what you get should not, at this point, at this microcontroller pin will not exceed your supply voltage. Okay, I'll give you an example about that also. So now what we will do is we will use one of these two, configure these 2 pins as analog pins. Let's go into the ADC section and see how we can configure it. Yeah, so these are the register. Results will be stored in 2 registers because this is an 8-bit microcontroller and the value is 10-bit. So in the lower 8 bit will be used, and in the upper 8 bit, this register only 2 bits will be used. And there is an ADCON 0 and ADCON 1. These are the configuration registers. Now let's quickly see how we can configure this. We'll just start here, ADCON 0. So before that let me create the source and header file. If you are directly coming here for a tutorial, it is better you go through all the tutorials so you understand what is a source and header file. If you already know that, then just continue with this. So we will have analog.h, and in source I will have analog.c. So here let me just include this. because this is required for using all the processor registers. And let me create a function initialize ADC. Okay, let's start configuring it. At con 0, just copy this, is equal to 0B. I'll do it in a binary level. Each bit I'll specify what it is. ADC conversion clock. So here what happens is this ADC module also requires clock signals for it to get the digital equivalent value. So what is the source of the clock to the ADC module? So different clocks are a frequency oscillation by 2. If you want some really fast, in your application you have to get the ADC value really fast, you can go for that. But you have to also make sure that this acquisition requirements are met, specifically the acquisition time. So what I generally do for this basic application is go for FRC, means there it will use an internal RC clock, so it is decoupled from my processor clock. So you can go to the data session and find out what is FRC value, how many hertz it is. So it is 11 channel select bit. Which channel am I going to use for clock conversion? So right now while configuring I will not worry about it. When I am acquiring the data I will use this 000. Then go done conversion start bit, means you setting this bit will start the ADC conversion automatically. If you set this bit, the ADC conversion will start. Then once the ADC conversion is completed, it will clear. So you have to, once you start, you have to wait for it to become to 0. Then you have to take the ADC value. So right now let me keep it 0. I am not using it now. Unimplemented read as 1 next value. Then ADC on bit. So do you want to power it on? Yes, I want to power it on. 8 1 2 3 4 5 6 7 8. So 8 bits are complete. So next is con 1 is equal to 0B right justified or left justified. So basically here what happens, the processor is 8 bits. So your ADC value is 10 bit. So it will need 2 registers, the result will need 2 registers. So I generally go for right justified because the lower 8 bits will be in ADRESL and the upper 2 bits will be right justified and in this register. So what I will do is lower bit plus 255 into this higher bit will get me the value. So I will right justify. Then conversion clock, so I will use FRC I will need, that is what we are planned to use. So here it can be either 0 or 1, so I can use 0. Then unimplemented read as 0. Then so we had decided, so here we have to tell which are my analog pins and what is my reference. So let's use a reference as VDD, that is the supply voltage, and negative reference as VSS for now. And I want 2 of the pins to be analog. So this seems to be a good option. So there is only one analog here, there is one analog here, 2, but that is using external reference. So this seems to be okay. V reference positive is VDD, negative is VSS. But there is one more pin which is configured as an analog, that is okay. It is 0100, 0100. Okay, this is done. So then let's just quickly go and see what other requirements are there, the registers associated with this. This is what I meant by right justified. All the lower bits and it will be here. Okay, just let's see. I think one more thing that we have to do here is we have to configure these 2 pins as input. There will be step by step procedure. configuring analog port pins. Tris bits as input. So the tris bits should be set as input. Input is 1. So if you are not sure, so I had covered this in my the first chapter where we are toggling the LED. You have to configure that as input or output, since analog is an input signal, so it should be configured as an input bit. So it is TRISA, tris A, because it is on port A, is equal to, I will make it all of them as input. So you can be very specific that bits dot AN0 is equal to, it's an input, and AN1 is input. AN0 and AN1, these two are my inputs. That is the analog port, and the digital port is called as RA. So to tris A0 and A1, I have to make it as input. I think that should be enough. So now this has configured it. So now let me prototype in analog.h. The next thing what I have to do here is I have to write a function to get the ADC value. Void, let me return the ADC value. I will not use any pointers here. Unsigned, I cannot use character because the result is a 10-bit value. Unsigned integer get ADC value. You have to pass which channel you want. Okay. So once you do that, so you have to set the channel here first. So that is adcon 0. So bits dot. So if you can just click on this, you can see the structure of that one. So this is a structure. I'll do a chapter on unions and structure. So right now I am using adcon bit, and I can use either specifically tell what is these three values. For channel 1, what I have to do here is go here and write 0 0 0 0, and for 1 I have to write here. But since it's inside a union, I can just set this, and it is 3 bytes. That it will also do. I'll do a chapter on structures and union. It will be very clear then how this structure is written and how we can use it. So right now what I'll do here is equal to the channel number. Then this go done bit I have to set. Setting this will start the A to D conversion. Dot is equal to 1. Then I have to wait until this bit becomes 0. Also make sure that this is not too long and your watchdog timer window is long enough. Let me anyway put it here so that while waiting for the A to D conversion, I don't want the watchdog timer to come and restart the again. Watchdog timer, I had done it in one of the earlier chapters. You can go check it out. So then once this is done, it is equal to 1 I have to do. If it is equal to 1, just wait here, and once the conversion is complete, this will become 0. Let me use a variable. Inside UC UI. This ADC value is equal to the lower register. This was a low register. You can again convert it into a 16-bit value and do bit manipulation. So just for the sake of simplicity, I will do into 256. So that will convert these two registers into a 16-bit register. And I will return UI. So let me prototype this. So let's see how it works. So let me go to main. I have to include my analog.h. So here let me comment all these things that we had used for UART. Just, this is closed. Yeah, it is closed. ADC code, so that you can use when I'll upload the code also. So I have to call first, before entering I have to initialize the ADC, then I have to call channel 0. So let me start with channel 0. So it's a good idea to hash define the channel. So I'll do it once I show you the demo. Let me have unsigned int a number here is equal to initialize ADC, not initialize this, get ADC value, and I'll pass the channel number. Channel 0 is, I'll do the conversion here. Then let me display this on the LCD also. 0 0. Then I'll do ADC, copy this. I'll have this number, or let me do it as ADC itself so that you don't get confused. Not right character, it is right long, comma 4 digit. Let me build this and check. It has built. So let's come to our Proteus. So here I'll connect it to this. So we had used this power. I'm not sure what the voltage is. Anyway, I'll put a voltage probe and find out what this terminal voltage is. Power. So I'll put a pot for the variation. There is already a pot here. Terminal ground. So it's a good habit in your actual hardware to use a small capacitor. Generic is there. Let me use this. So it's a good idea to use this one to avoid all the small noise that gets here. There will be part of this ADC line. So let me connect it here and let me start the simulation. So my ADC value should vary from 0 to 1023. Let's check it out. It is 512 because it's in the middle. So let me put a voltage probe also. Stop the simulation. One here, and let me put one here also to know what is the supply voltage. Let me start this. So it is 2.5 volts, I am getting 511. That is what we had calculated here. Okay. So if I increase the voltage, it will go to 1022, 4.99. The pot is not going to the full 5 volts. That's so 1022. If I come down, it will come to 0. So now this is how the ADC will work. So now now what has happened is you've only got the ADC value, still not got the voltage here. Okay, for that what you have to do is you have to convert it into voltage. So let me write a function itself which will convert it into voltage. And there is one more thing, it is always a good practice to average the value, means like average it around 20-25 times, so that you will see that there will be small ripples in the voltage waveform. So this ADC value will not be as stable as shown here, there will be some variations. So one, you can use this capacitor, or you can average it out, or do both also. So how to do the averages? I will just have to run a loop here. Assigned int counter is equal to 0 for UC counter is equal to 0. I'll average it 25 times. And after that, you have to make sure that it is not too high. You cannot do 100, because what will happen is when you add this 1024 100 times, what will happen is it will become 1 lakh. So a maximum value of an unsigned int is 75,000, 2 to the power of 16 minus 1. So you have to be careful about that also. Okay, so whatever you are averaging should not exceed the maximum capacity of the variable. So once it is done, is equal to divided by the number of times you have averaged. Let's quickly see that. Something is wrong. Let me find out what is wrong. Okay, I had to add it. I can do this because I was not adding it up. So whatever the latest value divided by 27, this is an easy way to add it. Else you have to do is equal to plus this. This will be in, try to put it in a bracket so it's clear. .511, and if you can go full negative. So now let me write a function to return the float value. Float get pin voltage. Function let me do, and let me just pass. We have the same thing here also. I'll pass this channel number. This in turn will call this float f is equal to, let me call this here and pass the channel. So now I have got the ADC value into a float. So now I have to convert it. So what we had seen was float is equal to 1023 divided by my reference voltage, that is 5, into the ADC value. prototype this. Now let me have one more. Since I'll have f volts is equal to, instead of get ADC value, it is get pin voltage, and I'll pass channel. Let me get it like that, ADC, then four, 5, 6, 7, 8, 9, 10 B. I'll have 2, 2. Is it B? Just check out the display chapter where I had shown you how to write the. This can be V is equal to, okay, showing 50 volts. Check out where the error is. Okay, I got the formula wrong. It is 5 divided 1023 into my ADC value. Getting 0. So something is wrong. 5.0. Sometimes these things happen. What will happen is it will take this as an integer. 5 divided by this will take it as 0, and into whatever value will again be 0. Maybe this is the issue. Let me just check. Yeah, I think that was the value issue. 2.4, 2.49. Yeah, that's good that it happens. So what happens is, generally when you are dividing something like that, make sure it's 5.0 itself, or if you have used a variable unsigned int, convert it into typecast into float. Else what will happen is, when it does the mathematical operation, that 5 divided by 1023, it will do it in the integer and not in a float. So then what will happen, 5 divided by 1023 into an integer is 0. 0 into whatever ADC value, it will become as 0 itself. Okay, now if you want to do this properly, let me define a couple of things. ADC reference 2.5, or sorry, 5 volts, 5.0. This is my ADC reference. Okay, then my just making it a bit more organized. And then also what we have to do here is, we have to define the channel. Channel ADC 1, you can name it as, for example, pot. Channel ADC pot as 0. So what I will do here, this has to be dot h. It will work if it is there also, but if it has to work from main, it has to be here. So now this is using the channel pot. not called, I think I deleted. Hmm. 2.49, 2.49. Okay, next thing what I have I'll show you is the ADC reference. So what happened was, till now what we were doing was we were comparing the analog input to the supply voltage VDD. So sometimes it is not useful. Let's assume that you have a relay in your board. Let's assume a 5 volt relay. Your ADC value is now correctly 5 volts. So your supply voltage is correctly 5 volts. Now as soon as you turn on the relay, what happens? The relay is a slight load, or if you turn on something which is higher, your supply voltage will dip slightly, maybe 4.9. So now what happens is ADC value will be calculated based on 4.9 volts of the processor. But for the ADC internal calculation, we have calculated to be 5 volts. So in these kind of cases where there is a chance of supply voltage fluctuating, either because of load or input voltage variation, then your ADC value will not be accurate. In that case, what will happen is we have to use external reference. That is one of the situation where external reference, you can give your own reference. Let me put a generator DC, and generally you can put what we use around 2.5 or 1.25. So let me use 2.5. And one more place where this will be also be used is, let's assume you are varying something which is very small, like varying from 0 to 1 volt. Then the 0 to 1 volt variation, if you are trying to catch in 0 to 5 volts, your resolution will become 1/5 already, because you are able to measure from 0 to 5 volts. The variation is only from 0 to 1. So you are only using a very narrow portion of your capability. In that case, what you can do here is you can use a V reference that is closer to 1 volts, that 1.25 or some voltage references ICs you will get. You can use those. So here I'm going to use I think I have set it to 2.5. Let me put a probe also. Let me start the simulation, and for this even though I have connected it, nothing should change. Why? Because in the configuration I have configured to use VDD. It is not that I have given 2.5 volts reference here and it immediately start to work. So in the configuration itself I have to go and change. See, we had used this 10100. Now I have to use this 0101. Then this third pin will be used as V reference. Okay, V reference will be AN3. AN3 is, I am giving the 2.5 volts. So this is ATCON 2, I think, or 1. So in my initialization I have to go to ATCON 1. I have made 0100. I have to make 0101, 0101. So now what happens, for the voltage should not show correctly. So instead of showing 2.5 volts, it is showing 5 volts, because there is one more place where we had to correct, that is in a calculation. In my calculation I had used, I am telling that ADC reference is 5 volts, it is 2.5 volts. It is being used here. That is why I hash defined everything, so that you can change in one place and it will work. Let me build this. And let me run this. See, now it's showing the correct value. Okay, if you want accurate value, because generally what happens is power supply ICs, there's primarily for power supply, there will be some variation in them, but voltage reference sources are specifically designed for that. It will be super accurate. So if you in your ADC, if you want to be super accurate, you have to use external reference, and in some cases you will also use V reference. So right now what has happened, at 0 volts it is giving 0 ADC, and at 2.5 it is giving 1024. So in some application like a Wheatstone, a weighing scale or something, the output voltage might not vary from 0 to 5 volts or 0 to 2 point. It might just vary around 2.5. Let's say from 2.4 to 2.7. So at that time, to get a better resolution out of it, we reference negative, you can connect to, like for example, a 1 volt, and positive you can connect to 3 volt. So now this 2 volt variation you will get 1023 resolution. Okay. So now there is one more thing which I have to show you, that is when your supply voltage is, or the sensor voltage is higher than 2.5. Let's assume my sensor voltage is, I can generate up to 100 volts. Place some generator DC, it can generate up to 100 volts. Then you cannot connect this directly to this pin because this pin will fail. Then what we will use, we will just use a potential divider. You can use R. We use also capacitor, as I told you, a filter. Generally we will use it. This is hardware debouncing, not debouncing, hardware averaging, or you can do in the software where it took 25 samples and averaged it out. Doing both is always better. Component, capacitor. So I forgot, generally 1 nanofarad is kind of useless, 1 microfarad let's use. It all depends on like your application. 0.1 also will be enough. If you put too much capacitor, then what will happen is your voltage will be varying fast, because this capacitor has got charge. This capacitor voltage will not vary, so you cannot see any variation in the voltage at all. That one you have to be careful. Microfarad, and I have to step it down by 100 volts. I have to step it to 2.5 volts. So it's always better to use a very high value, so that the current dissipated in this resistance are very less. 100k, 10k, 10 times it will divide, I'll get 10 volts. I'll use 1k. And let me connect this to channel 2. For channel 0 we had used, let me use channel 1. Terminal, ground. So in my code I have to go and change it. So port is 1, external volts be channel, this is the next channel. I need to do it in the second line. Put a probe also here, the supply, and which is going to the microcontroller pin. So 100 volts got converted to 0.1 volts. So I didn't change the locations, writing on the same locations. So let me make it 40. 40, not here, 40, 44, you are getting 0.99, 0.98, but you have only got at this value. Now this, because of this division of 10, I have to multiply, I have divided it by 100 because of potential I have to multiply it by 100 times here, so I have to multiply by 100 there. So 2 won't work, it will be 3 comma 2, and f holes I have to multiply by, this is like a quick way of doing it, f holes, or you can is equal to f holes into 100. Let me run this. See, 98.9. So just a minute, I think the formula is so the formula is V out is equal to R2, that is then R1 plus R2 to V in. So if you consider this as V out and this as V2, that is what I am considering. So now I want V in is equal to R2 plus R1, that is 101 divided by 1. No, 101, it is not just 100. It is a potential divider formula, I just missed that for some reason. So it will be 101. So the basically what happens here is it's not getting divided by 100, it's 101. So V2 if you see is R2 into R1 plus R2 into V in. That is why this error was coming, it is not showing the correct voltage. So 101, let me build it, 99.9. So this is when you have DC. In some cases what will happen is you might have AC voltage, it might not be DC at all. So then what we will do here is we will just use a simple half bridge rectifier. Let me have generator sine. So this is when you want to sense your supply voltage. V sine RMS is 220 volt, frequency is 50 hertz, a diode, then I will use the same potential divider here. But it is a good idea to use a transformer, step it down and also provide the isolation, else what will happen is this point on the board will be live. But in small applications you can directly use it. Terminal ground, connect this. So bulk of the voltage will be dropped here, and this resistor I will use for tuning. So let me put a capacitor also. So now I have to use a bigger capacitor because I have to convert the sine wave into a constant DC. So if you see our diodes chapter in basic components which I had done, I had shown you how to do this. Let me use a capacitor, so I will use a bigger capacitor. I will put a scope and show you what is happening. So let me use a 10 microfarad capacitor, and then I will connect this to that. me delete off this line. I'm not deleting the component because I'll just leave this simulation file in the description below so that you can take that up. So let me put a oscilloscope also, so we will know what is happening with the waveform. So let me have one, let's have all three. 1, 2, but this will be off scale, so you might not be able to see that. 3, I'll put a probe also here. Let's see. This is the point where we have given it to the ADC. So I also have a oscilloscope chapter. So if you are don't know how to use the oscilloscope, please check it out. Like both the voltages are off the scale. 20 volts. I cannot go below per division 20 volts. It's more than that. That is why it is not able to show that. So let's just turn off ground. I've given it to, you see it's varying in, this is a 1K pot, that is the issue. This value is very low. So let me change it to a 10K pot. Then let me run the simulation. 0.4, 0.5 volts is coming. Still there is a lot of variation. Increase the capacitor or increase the value of resistor, that variation will go away. Channel C, give DC. This is my variation level. So still there is a lot of, let me ground it and put it to a point. Let me put the ground over the blue line. So this is the reference. Let me give DC. It is not filtered properly yet. That is why you are getting this variations. It's varying a bit. So if you want to even stop that, what you can do here is either increase the value of this, or you can go to higher value of capacitance, like for example 0.47, 47 micro. The ripples have come down. If you see here, this variations would also have come down. So now what you have to do is, this one you have to link it to the supply voltage. So into 4 or 5 will find out what, practically put a multimeter here and decide the multiplication factor, and over that if you want some more fine tuning, you can do this or not even use the pot. Okay, and the last bit of tuning if you want to do in the side, like just slightly change the, if you were showing for example for 220 it was showing 240, you can just tune this one so that you get exactly 220. Hope you are able to understand that. We were also parallelly checking out how the code generator will also work. So let me set it to the set as main project. So here if you go source, MCC generated file, so here the ADC file will come up. So for that let me launch Microchip code configure. So let's see how the microchip will write the driver. I cannot simulate this, but I'll just quickly show you how it will do it. I have to add ADC. So ADC has come here. Clock source, FRC, right, positive reference VDD, negative reference VSS. These are all the things that we are doing. Enable interrupt. If you want to, like after the end of the conversion, if you want to enable interrupt, you can do that. So let me generate the code. So it has generating the file. If you go to files, project view, so you should have ADC. So ADC initialize. So this processor has a lot of registers like ADCON1, ADCON2, ADCON3. So many registers are being done. This start conversion, the add on bit that we had set, that one, and this also seems to have add on is turn on the A to D. AD go will start the conversion and you wait until this conversion is complete. So get conversion, you turn on the module channel, you set up the channel, turn on the module, then start the conversion, wait for the end of the conversion. And if here they are starting and stopping the conversion, it is better to do that, because if the ADC is module is on, there will be a bit of power consumption, around 2 to 3 milliamps power consumption will be there. If your circuit is very power sensitive, then it is always better to turn off the ADC module when not in use. Okay, so they have done a lot of registers. You can go through them, but the basic is what we had done earlier. You should give it a try. I am not sure if this is simulatable in Proteus. You can select a processor which supports MCC and also simulate in Proteus. You can do that, or else if you have hardware, you can do that. Okay, now let's see how we can use ADC module in the Renesas controller. So if you have come here particularly for the Renesas, please watch the microchip section, because that is where I have explained a lot of how to write the drivers and all the functions. Here I'll just copy paste and just briefly talk about it. Okay, now this is the same board which I was using last time. So this is the schematic. So this is one of the boards where I am sensing the line voltage. So what I have done is, in the simulation I shown, I use a diode, multiple resistors to drop it, and a pot to tune it, and a decoupler and a capacitor to filter out the AC waveform. And this AC sense I have given to this ANI1 analog input channel 1, and I don't have a positive reference. So in our example we are done without and with a reference voltage. Here I am not a very critical, it's not an application where the voltage had to be super accurate, so I am not using the ADC reference. I am just using the VDD, which is 5 volts. Okay, and my channel is AIN1. So now let's see the code configure section. So if you come here, this is the same project which we had last used for UART, and before that LCD also. So you have to come here, A to D converter, you have to use used, and the comparator operation is required for the ADC in Renesas. You can go through the datasheet and know more about it. It will be in operate. Resolution 10 bit or 8 bit, we will go for 10 bit. Reference, positive reference, we will go in for VDD. If you have a negative, if you want a reference, you can connect it to this reference, V reference positive. This is where you have to connect it. In this application we don't have that. Then continuous select mode, you want to be continuously selecting the channel for conversion, and also tell which are the analog channels you are going to use. I can use only these two because my channel is on AIN1. Then that should be enough. So generate code. When you generate the code, there are three files which come here: adc.c, adc user and adc.h. So now let's write our code, like how we have been doing with all the .c and .h files. Let me do that. Header file. Let me do analog.h. and just copy this. So here I'll do. And all these things, see the earlier chapters to figure out why I am doing this. And adc.c, source file to analog.c. Here let me include .h, and we have to also include few of the drivers that this is included. So specifically this ADC and this micro drivers and ports. Okay, next is we'll do initialize ADC. Let me put prototype in analog.h. Again, check out the Microchip chapter or earlier chapters why this .c.h file is required. Then here inside initialize, to initialize what we have to do here is, if you go to ADC create is something which it calls, and ADC start is what you have to call to start the ADC and stop ADC. So analog.h, this is the only thing that you have to do. And if you go to ports and see, this would have automatically become I think which port we were connected to. It will show in the port, that is P2.1, port 2.1. So it is telling it is used in analog. So you don't have to do it as input or output, it will just do it by itself, the driver. Okay, here then I have to include analog.h. Then before getting into my while one loop, I have to initialize the ADC. This is the only thing that you have to initialize. ADC, yes, it is analog.h. Showing a lot of errors. Maybe here will prototype. This sometime happens. So what I figured out that if you put this in .h also, it doesn't throw up all those errors. Let me just check. Clean project, build project. So it has gone away. I've seen that with CS+. Sometimes it throws up all these weird errors. Next thing is, in the ADC we have started the ADC module inside the processor. So the next function that we have written in the Microchip is, let me see here, analog.c, we have written get ADC value. So if you go to this, the exact thing. So what we are doing here is, we are averaging the ADC 25 times. That is the for loop. I had explained this in Microchip. You can go and check it out. And all these bits will. So this is the code. So this is the channel. This is the internal microcontroller register where you have to load the channel, and there is a flag. So if you clear this flag, the ADC conversion will start, and once the ADC conversion is complete, this flag will be set. So you have to wait in this while loop. Okay, then what will happen is, this is the register where the ADC value is stored. So this is a 16-bit register and the register convert the higher 10 bits. The 16-bit register, this is a 10-bit register. So, in the 16-bit register, the higher 10 bits have the value and the lower 10 bits are 0. So, basically it is left justified. So, left justified, what happens is it will not, I cannot use it directly because it's a pretty, it will be a pretty high value. So, I have to move it by 6 locations so that it is right justified, then I can read the value. Okay, I think why they do that is because if you want only to take the 8-bit value, then you can just use the higher 8 bits of this. You can use this register, but I am going to use a 10-bit register. So, I have to right justify it so that I can directly use it. If it is left justified, then the LSPs are 0 and the MSPs has some value. So, the value will be very high. If you right justify it, the LSBs are filled up and the MSBs are 0. The 6 MSBs will become 6 of the MSBs will become 0. So, I will as I told you in microcontroller, it is always a better idea to loop it, like take the value about 10, 25 or something, so that you remove the ripples. Then, so that is why this for loop is done, and after that I divide it by 25. So, now if you come to, now this is a function I have to use. Let me prototype it. Use it in the main. So, if you don't initialize this, if you don't start the ADC register, then what will happen is you will get stuck here, means this flag after clearing will not be set if you don't start it. So, then what will happen, your watchdog timer will come and restart the processor. So, make sure that if you see that while coding, if any ADC your code is hanging, then basically you are not initialize the ADC. Okay, now this is the channel which we have to call. So, this is the channel, and our channel is 1. So, let me, and this has to be loaded into a variable. So, let me paste it, then let me make it UI ADC value. Let me take it inside this. Now, let me run the code. There are no errors. So, let me put a breakpoint here. Let me see what happens. So, I am just debugging all the registers. So, 729. Oh, sorry, 479. So, let me run it. So, I will just slowly turn the pot and you can see that ADC value change. So, that is the max. If I come down, it should start falling. You can see that it is falling. Okay, because I am changing the pot, the voltage that is going into the reference, into the ADC pin is changing. So, what I have done is basically I have connected this to a fixed voltage, and I am varying the pot here. So, once I start varying the point, this voltage will start changing. So, that is how you implement the ADC. So, now let us see how to convert it into the float as we have done in Microchip. I will just copy paste that code from there. Analog.c, let me paste it here. Let me prototype this. Then we had a few more things in analog.h. These things we were using for the calculation. So, here my ADC reference in the microchip I had connected a 2.5 volts reference in Proteus to show you. Here it is 5.0, it is connected to 5 volts. Now, to get this I have to call main channel 1. Let me have a variable also. So let's run this quickly and see. Let me put this to watch here. It is 2 volts. Let me check on the multimeter what voltage it is. .02. Here it is 1.99. So 2.0. So you are getting the voltage. So that is how you use the ADC module. Hope it was clear, and in the description below I will have all the codes, the Renesas, the Microchip and the Proteus simulation. Hope you guys were able to follow that.